Good morning and welcome to the CXL presentation where we're going to go over devices and ecosystems. My name is Curtis Bowman. I am the chair of the marketing group for CXL, and I'm joined with Sandeep from Astera Labs, George from Elastic Cloud, Kapil from Samsung, and JP from Xconn. Let me start real quickly by going over just a quick overview of what CXL is. And it starts off with, why do we need CXL? Well, a group of folks got together, and the companies they were working with said, hey, we need something that is a much faster interface than what we currently have in systems. We need it because the systems are starting to use heterogeneous compute. They need more memory capacity, and they also need more bandwidth. And so from there, we opened up the CXL Consortium and made it so that what we had was a very coherent, low latency, high bandwidth, easy to implement interface that the industry could use and have that compatibility as we move through devices. When we first launched, it was CXL 1.1, and it was really intended to be inside the node. So just a point-to-point solution. And we defined three different types of devices. We defined the type 1 device, which was really an accelerator or a NIC that was self-contained and didn't have any need for memory on it. It actually started to use memory from the CXL device that was attached to. Type 2 devices, a little more complex. They actually have their own memory, but they also can access memory onto the CXL network. And so you have two spaces of memory, and you can share those between the host and the device that you're using. And then the final type was a memory buffer, where it allowed you to increase your capacity, increase your bandwidth going into your, whether that could be an accelerator or a host. And it also allowed for using different types of memory out on the memory bus. Then came 2.0. So we introduced 2.0 in 21, and what it really added was the ability to do switching and also pooling. And so you see in the pictures here where we have the different devices, different memory devices on the bottom with hosts on the top. When you pool them, you can put a device per host, or you can break them down into subsections and put part of the pool to one host and part to another. Then as we went to 3.0, we actually went to full sharing, and we also went beyond just one switch level, so we could do a full fabric. And so what it really allows you to do now is take any device and share it across the network with other hosts. You can also access memory in a standalone fashion, and you can share that memory, physically share the same location between hosts or devices. So that's just a quick overview of CXL. If you need more information, we have that available on our website. Great tutorials there. And you'll find us on a number of the social media platforms. And our YouTube channel has a great number of videos if you want to know more about it. So with that, let me hand it off to Sandeep, who will go over the next portion of our presentation.
Thank you, Curtis. Hello, everyone. And I appreciate the opportunity to talk here. As Curtis talked about the scope of CXL and various protocols it supports, I want to focus a little more on how Type 3 memory controllers in particular plays a significant role in heterogeneous compute architecture. One of the major improvements in modern day computing is introduction of heterogeneous and composable architectures. And that's an advancement data centers and cloud service providers very much needed because it provides the ability to separate memory from compute resources, makes it composable and flexible. Why is that important? With that level of flexibility, data center managers can scale memory as needed with other components of the systems rather than simply being tied to the processor itself. The diagram here shows memory and storage hierarchy, which it has remained largely unchanged for the past several decades. Data centers usually store and archive data in storage devices, which has higher capacity, but of course, that comes at the cost of increasing latency. Inversely, if you look at the diagram here, the higher you travel up the memory and storage hierarchy, memory has lower latency and increasing bandwidth. So we really need a memory tier which kind of balances between the cost as well as latency and bandwidth. And that's where CXL protocol comes into play. Especially type 3 devices in particular adds a layer of memory between near attached memory, which is the traditional direct attached memory at the top, and the far attached memory or storage devices at the bottom. The advantage here, as I stated earlier, is it provides higher bandwidth and faster speeds than fast storage, which is very much needed for AI and ML kind of workloads. And at the same time, it's more affordable due to its memory pooling capabilities. And I'll talk a little more about memory pooling and sharing in the next slide. So that's a good segue to look at the technology example of a type 3 memory controller. So let's jump to the next slide. What you see here is Astra Labs Leo memory connectivity platform, which is a type 3 CXL 1.1 and 2.0 memory controller. And that is purpose-built to address memory capacity and bandwidth bottlenecks for AI, ML workloads that the cloud servers depend on. As you can see from the system block diagram, it supports memory expansion as well as memory pooling and sharing for heterogeneous architectures with multiple CPU and GPU topologies. I mentioned memory pooling earlier. With memory pooling and sharing, one of the advantages is you can prevent memory stranding through effective utilization of memory resources across multiple hosts. Since this can eliminate the need for over-provisioning, we reduce the overall TCO as well. Other features that Leo includes are multiple DDR5 channels to increase memory capacity up to 2 terabytes. What's equally important is Leo has server-grade customizable RAS and software features that can easily be integrated into fleet management services that data centers and cloud services rely on. It also has best-in-class industry-leading security features. As you can see from the product offering at the bottom right-hand corner, it is offered as SoCs as well as board solutions as well. To learn more about Leo and product variants, please visit our website at astralabs.com. And with that, I'll pass on the baton to Kapil from Samsung.
Thanks, Sandeep. Hello, everyone. My name is Kapil Sethi, and I work as a Senior Manager, New Business Product Planning at Samsung Semiconductor. So let's focus now on a typical Type 3 memory expansion device, and then I will also talk about what Samsung is doing in this space. So a CXL Type 3 device has a memory controller and attached memory. Type 3 devices do not have compute logic on the device side that can modify the content of the memory. Rather, the CXL Type 3 device enables different types of memory media to be attached to the host through the CXL link. An important point to note is that the memory attached on the CXL device is mapped coherently to the system address space. So what it means is that the CPU and the device see the same data when they need to access it. CXL.mem transactions are byte addressable load store types of transactions, just like a DDR, whether it's DDR4 or DDR5 memory. So the attached CXL memory looks like natively attached DDR memory to the end application. Moving to the next slide. In this slide, we will see how a CXL Type 3 memory expansion device helps to increase system memory capacity and also memory bandwidth. So the conventional way of adding more memory capacity and memory bandwidth in a system is by increasing the number of DDR memory channels and by increasing the data rate of the memory. But each of these techniques have their own significant engineering and also business or cost challenges. Now, let's look at how memory density and bandwidth can be scaled using a Type 3 CXL memory expansion device. So on the left side of the slide, we have a hypothetical system which includes a CPU with 8 DDR channels, considering a 2 DIMMs per channel system and each DIMM being 512 gigabyte. The total memory density of the system is 8 terabyte. Now, on the right side of the slide, in addition to the 8 DDR channels, we also have 4 CXL links. with each link supporting up to 1 terabyte of memory. So the total system memory capacity is now 12 terabyte, and additional CXL links also increase the total memory bandwidth of the system. So this is a very important achievement, as the CXL memory expansion device provides a flexible option to increase the memory capacity and bandwidth of the system without increasing the number of primary DDR channels or increasing the memory data rate. Now let's pivot from the CXL Type 3 memory expansion device overview to what Samsung is doing in this space. So I'm very excited to announce the development of CXL-based DRAM memory expander product built with an application-specific integrated circuit CXL controller. This memory expander product we believe, will pave the way for the commercialization of CXL technology. In terms of some of the key features of Samsung's CXL Type 3 memory expander device, the new memory expander device comes in EDSFF, namely E3.S2T form factor. This form factor makes it ideal for next generation high capacity enterprise servers and data centers. The memory expander module comes in memory densities of 128 gigabyte and 512 gigabyte with DDR5 DRAM memory as the media behind the CXL interface. It uses a by-8 PCIe 5.0 interface to connect to the CPU. It also supports CXL RAS features like viral poisoning, memory error injection. And in terms of availability, the samples are currently available for early evaluation and testing. Now, in the last slide, we will review some of the test results of memory expanders with commonly used artificial intelligence and machine learning applications, namely BERT and NASNet. So the charts that you see on the slides here compare the performance of DDR only versus CXL memory and DDR populated in a system together. To summarize, what we have seen is that when DDR and CXL memory expanders work together in a system, with some of the models instances running on the memory expander and some on the natively attached DDR, the inferences per minute, or IPMs, increase by 100% for BERT and 45% for NASNet models, respectively. So with that, I would like to pass the torch to my friend JP, and he'll talk about the cool technologies he and his companies have been working on.
Hey, thank you, Kapil. This is JP Chen. I'm the VP of product at Xconn Technologies. So Xconn Technology is a startup in Silicon Valley. We started 3 years ago. We focus on doing the CXL switch and the PCIe switch. So we already have our first silicon in our lab already over half a year. So this is the world's first CXL 2.0 switch and also a PCIe Gen 5 switch. The switch has a total 256 lanes with a total capacity of switching capacity 2 terabyte per second. And we're purposely built for this CXL application, memory expansion, memory pooling. So the port latency is the lowest in the current industry. And also our chip optimize all the design to have the lowest power consumption. So the chip already been working with the current shipping CXL 1.1 processors. And also we do a lot of interoperability with the CXL memory devices, and they all work well. The device is also going to be future compatible with the upcoming CXL 2.0 processors. So a lot of work is undergoing. Then also remember this chip is a PCIe 5.0 switch. Another good thing about it is the chip works in hybrid mode, because we see in the future there's a coexistence of PCIe and the CXL for a longer time. So having both capability would really benefit the system design. So engineering sample for the chip is available now. So let's move on to the example of this application. This is a simple illustration of what the switch can enable memory expansion. So we say it's scalable because the switch can plug into any kind of CXL CAM slot or PCIe slot to expand, and also the switch can further cascade to form a network. So you can see here, with our switch, we can easily expand the memory footprint by another 30-fold. And if you do more switch, that's another multiples. So that's an advantage of using a switch. So next page. So this page is talk about the memory pooling. I think memory pooling is the one that industry is going after, because the memory pooling will realize a lot of benefit. For example, previously, Kapil and Sandeep all mentioned about all these memory bottleneck, stranded memory, these issues. With this scalable memory pooling enabled by a switch, you can see you can have a very big pool and being shared by multiple server hosts. So the picture on the left is actually the current status, because the processors, they are CXL 1.1, and the devices either CXL 1.1 or CXL 2.0, but our switch all work with these devices. And in the future, our switch will work with the MLD device and the SLD device. Also host can be 2.0. And our switch support a Fabric Manager, standard spec-defined Fabric Manager interface. So next page. This is a picture just to show you some hardware we already have. So as mentioned, we have the silicon in our lab, and we also have a couple reference design. So the picture on the left is our initial reference design board, the switch board, but we already advanced to the new rev of this reference board with a much simple design and a much smaller heatsink. Next page. So the CXL, all this memory expansion, memory pooling, it's already going on. We are already working with some of the leading hyperscalers and the leading OEM and ODM to design some prototype system to target for the testing and software development. So this picture is one of the design we had with our customer. So you can see our switch is being put into a chassis, which has a lot of parts just coming out. And the chassis support a CPU and a BMC. So the CPU will enable a lot of Fabric Manager functions, and the BMC manages the board. And on the right side, you see a box with a full rack of memory, CXL memory. These two boxes can connect through a CDFP cable, and then a lot of testing and development can happen on this platform. That's all my presentation. I'll introduce George for the next presentation. Thank you.
Thanks, JP. Hi, my name is George Apostle, and I'm the founder and CEO of Elastic.Cloud. The genesis of our company, we started 1.5 years ago, and most of us met while working at a company called PLX Technology, where we pioneered the PCI Express switches in Gen 1, Gen 2, and 3. And since then, there's been several other generations of that switch released in the market today. So as we started looking at CXL and the capabilities of CXL, what we saw was it really expanded on the capabilities that we looked at while developing PCI Express. The challenge that we had with PCI Express was how to bring that technology up into optimizing the overall system level connectivity and performance. And we tried with SRIOV, which one could say was pretty successful, and then also with MRIOV, multi-root IO virtualization, which posed a real challenge because of the PCIe protocol and the limitations of that protocol. It was difficult to have multiple processors now connected to these IO devices. So today, as we move forward in heterogeneous computing, what we see is it is really important for these endpoint devices, and we call, they could be anywhere from accelerators, GPUs, TPUs, XPUs, to SSDs, to memory, and even NICs, all connected together. And the question then became, how do we manage all of these devices from a system level standpoint? And so what we're looking at is not just connecting these devices to processors, but also the management of those devices. How do we create a fabric manager that can then manage, the ecosystem of components that are connected to a switch? How do we connect those switches together so that we can expand these in terms of fabrics? And what kinds of things can we put into our smart switch SoC in order to help these systems improve overall system performance, right? And this includes things as fabric managers to manage those interfaces, connecting to standard orchestration software that has been developed over the last few decades, and to be able to connect, and not just connect, but also configure and reconfigure those devices that are connected in order to create optimized virtual servers that can then get better effective use of those devices in executing workloads. So inside the chip, as we're designing, has a number of hardware accelerators to help with the data transfer and the requirements of those data transfers. Smart caching in order to hide some of the latency that these devices will have as they're connected to multiple heterogeneous compute environments. A switch, obviously, so that you can have the connectivity and peer-to-peer capability that is provided in CXL 3.0. And then also being able to expand that over different types of medium in order to get better efficiency both inside the rack and rack to rack. So the scope of what we're looking at is on the next slide. You'll see there's sort of three scopes that we're looking at. One is inside the box, where we want to expand the resources inside the box to be able to connect to a number of different devices. And then in the center is sort of the more resource pooling type of device, where you've got maybe blade servers that plug in the front with different kinds of compute and elements connected through a mid plane, where on the backside you're plugging in either DIMMs or SSDs or other accelerators associated with that, and be able to manage those devices through connectivity in the switch. And then finally, the third one is when we're looking at a fully disaggregated rack, where we have pools of resources contained in that rack and all connected via a switch, top of rack switch, that can then allow access to these pools of resources from the other smart elements. So doing this is sort of an evolution of the CXL spec, and the good thing about that spec is that it does maintain backwards compatibility. So it allows us to do kind of forward implementations of the spec. Even though we're only in a 1.1 environment today with processors, we can provide some of those 3.0 features today that we know are going to be around over the next several years as the CXL spec evolves. So we're demonstrating this functionality today in FPGA, and as we continue to to work on the ASIC that will provide this connectivity throughout the ecosystem, and working together with all of the ecosystem vendors to ensure we have this capability built into building more of these optimized system architectures. Thank you.
All right. Well, thank you everyone for attending today. Thank you again to Sandeep, Kapil, JP, and George for joining us, and thank you to your companies for their continued support of CXL.